Hello everyone, this is Doug, and in this video we are going to look at part 3 of our discussion of alcohol oxidations, specifically just a couple of greener oxidants. So like I was saying before, right, there are so many different ways to oxidize alcohols. There are whole books on it. In this video, I just want to talk about a couple of greener versions because we do care about green chemistry, we care about the environment, we care about our own health and safety. In this part 2 of this series, I mentioned PCC and the Jones reagents, and we talked about how those are chromium 6 oxides. And the problem here is that chromium 6 is super duper toxic. And so we really want to avoid using chromium 6 because no one wants to use it and it's expensive to get rid of. So people are trying to move further and further away from it. It works. It's fun because it changes from like green to orange, but it's just a terrible reagent to use. Useful, but hazardous. So then we have other things like this, for example, which is called the Swern oxidation, which is much greener, and it has, most importantly, no toxic metals. And so we're going to talk about the Swern in a little bit more detail here and remind you about things like oxone. So just like we were talking about how there are strong and weak oxidizing agents, we were talking about the chromium stuff. And with those, really the only difference was, is there water present or not? And you can kind of keep that same mentality here for oxone and Swern. Oxone almost always has water associated with it because it's water-soluble salt. Swern never has water present. You got to keep things real dry in order to do Swern oxidation. So let's just kind of review a little bit about those and look at an example here. So oxone, my students, you all have already used this in lab. It's called a triple salt. This is the main oxidant here, the per-sulfate. So this is a per-sulfate, right? Because it's SO, not SO4, it's SO5, which means it's got an extra oxygen, right? So per-sulfate. It's just got a peroxide in it, which is what the oxidizing agent is. So it just allows that to be the oxidant. What's nice about it is it is a really easy to use solid. You just measure it out. It's a white powder, easy enough. And then water, like I said, is present, and it's usually there so it can dissolve your actual oxone. So it's just there to dissolve the oxone. But like we learned before, because there's water present, you can form a hydrate and you can fully oxidize. So it's there to dissolve the oxone. But what this means is that it can fully oxidize to the carboxylic acid. Whoops. Oxidide, it's not a word. Oxidize to the carboxylic acid. Right, which is exactly what we see here. We have a primary alcohol. If you add oxone, I use ethyl acetate in water like we did in class, then the idea is that it could go all the way up to the carboxylic acid, right, your CO2H. It does not stop at the aldehyde. You can use it to take secondaries to ketones, but the idea is that we treat it like a stronger oxidizing agent, and you can just kind of keep on going all the way to the carboxylic acid. Now, the Swern oxidation is a kind of a different beast. It's a two-stepper. You'll always see two steps. So step 1 and step 2 here. Note that this stuff is not all mixed together. If you mix all this together, it does not work. The reaction is not going to happen because you're going to screw up your reagents. So the first step is always DMSO, which is dimethyl sulfoxide. So dimethyl sulfoxide, which is just that was your sulfoxide and then your DMSO, so add 2 methyls to it to make it a dimethyl. Dimethyl sulfoxide. Let me get that methyl a little better for you. So that's DMSO. That's one of the parts of the reagent. I debated going back and forth whether or not I want to show you the mechanism. You can look it up if you are dying to know, or you can ask me, and I'm happy to make a video for it, but I'm not going to hold you responsible for it, mostly, again, because this is a crazy COVID term, and you're not going to see it on the ACS test, so let's not worry about it. Let's make our lives a little more simple, but it is a really cool mechanism, and the DMSO is not the solvent here. It's an actual reagent used to help oxidize the reaction. And then you also have oxalochloride here, which is abbreviated as this. This is your oxalochloride sometimes. So sometimes you'll see CO, Cl, and then in parentheses 2. And because that's supposed to mean that you have a CO and a Cl, So it looks like an acyl chloride. And then there's two of them. So then you have another CO double bond and another Cl. So oxalochloride is a symmetrical molecule. It's 2 carbons, 2 oxygens, 2 chlorines. And that's another part of what makes your oxidizing agent in that first step. And what you'll notice is that these are always cold. So the Swern oxidation is always going to be at low temperature. So I'll put low temperature. In this case, I mean, I put negative 78 degrees Celsius because that's the temperature that I used when I've done Swern. It is a fairly common one for Swern. That just means that it was done in a dry ice acetone bath is the idea. If you saw negative 50, that would be fine too. Or even lower would be fine. It's just got to be really cold. The idea is it's really, really cold. And then what you do is then the second step, and this is where the actual like oxidation occurs, is that you add TEA. And if you don't remember, TEA is just triethylamine. So triethylamine, that's going to be the base that plucks off the hydrogen that's on the carbon where the OH is. So triethylamine, right? So nitrogen, 1, 2, 1, 2, 1, 2. So you got 3 ethyls on your amine there. And again, one way to kind of remember that the Swern oxidation only oxidizes up to the aldehydes is that there's no water involved in this whatsoever. You got to keep this very, very dry. I always flame dried my glassware to make sure I didn't have any water at all. Use really dry solvents like dichloromethane or something like that. I always made sure it was dry. But it's a great reaction. It works super well, super reliable. It really saved my life when I was doing my research in grad school. I had to try to oxidize, actually the molecule on the slide before this, and nothing worked but Swern. Swern was just a lifesaver. Loved it. Love it, love it, love it. It's a little stinky because it makes dimethyl sulfide, but you know, I'll cope with that. So let's take a look at a couple of examples here. So now if I'm taking a look at these, first example looks like I got some sort of benzylic alcohol here. Again, so I made this look just exactly like the stuff that I showed you on the previous page. This is definitely Swern. It's definitely Swern stuff because I see the DMSO, the oxalochloride. I see 2 steps, and I see triethylamine in the second step, and I see that it's cold. It's totally Swern. So that means I'm just going to oxidize this once. So oxidize only once, right? So even if I could oxidize it multiple times, which in this case I can, right? Because I've got 1, 2 hydrogens here. This could be oxidized all the way up to the carboxylic acid, but I'm only going to oxidize it up to the aldehyde because we're using Swern here. And Swern does not oxidize all the way up to the carboxylic acid. It stops at the aldehyde. So I'm just going to draw the aldehyde. Now, if I look at this second example here, it looks like I've got oxone. And sometimes you'll see, and I'll show this in some of my examples, sometimes people just say Sometimes people will just say oxone. Like they know what they think that you know what they're talking about, which is fine. We can just say oxone. But the idea here is if you see oxone, just go ahead and assume that there's water. So I'll say assume the water is present. Unless you see something that says explicitly otherwise, just assume water is present because, again, that's usually what we dissolve oxone in is water, which means then I'm going to fully oxidize. I'm going to fully oxidize any alcohol I can. So here I have a primary alcohol that looks like I can oxidize twice. Here I have a secondary alcohol that looks like I can oxidize once. And so for my product, I'm going to do exactly that. I'm going to draw my cyclopentane piece. This alcohol got oxidized up to the ketone, and then the other one got oxidized up to the carboxylic acid. Right, so I'm just fully oxidizing all of them. I'm not worrying necessarily about like equivalence or anything like that. I'm just oxidizing them as far as they can go. Now again, so we'll go to this third example. Here's a little bit more information. I see again the oxone and water and acetone are explicitly written out. Okay, great. Go over here and it looks like I've got a tertiary alcohol, which means I know that I can't do anything. I still can't oxidize tertiary alcohols, right? You'll never oxidize a tertiary alcohol. So it didn't matter if I put oxone here or Swern, not going to happen. And then lastly, let's do one more. Here's Swern. So again, if you just see Swern or a practice problem asks you to like do the Swern oxidation and doesn't show all the reagents, same thing, right? Just oxidize it one time. Again, we have a primary alcohol, so I know that I'm only going to have it go up to the aldehyde. I'm not going to have it go to the carboxylic acid. So I'll just redraw the structure, the carbon backbone, and draw my aldehyde there. And that's it. So there's 4 examples of using those much greener oxidants. And again, the big key thing here, right, is that all of these, they have no toxic heavy metals. Which is generally why they're considered to be relatively green. Now, there are some problems with DMS, with the Swern, because you have to use really low temperatures, so it's kind of an energy hog to get things down to -78. And then the production of oxone also takes energy, so there's some embedded energy costs, but they're pretty straightforward, pretty easy, pretty low toxicity reagents. So they're much greener, much better, though, than chromium-6. That's the point. So go ahead and do some practice with this. If you have any questions or comments, please leave them down below. Happy studying. Good luck.